Do you have a favorite prime number? 7. So, who's got a favorite prime number? What's your favorite prime number? 5. What's yours? 13. Oh, that's a good one. That's a good one. Yes, ma'am. 59. Awesome. So, you know what's special about prime numbers? They're kind of the atoms of numbers. What's an atom? Wow, good point. Everything's made out of atoms, right? What's an atom?
2 molecules combined together?
Yeah, well, when atoms come together, they make molecules, right? So if you're walking down the street, right? Walking down the street and you run into a oxygen molecule and it's got 2 hydrogens stuck to it and it kind of looks like Mickey Mouse. You know, you're walking down the street. You know what that's called? H2O. You got another name for that? Water. Yeah, and if you're walking down the street and you run into another molecule and you're very special, right? Because you can actually see the atoms. You're really small, so you're subatomic. But you're walking down the street and you walk up and there's 2 oxygen atoms stuck together holding hands and they got 2 hydrogens. You know what you call that? H2O2. Bingo. Who said that? You nailed it. Does anybody know it? There's a special name for another name for H2O2. I don't expect anybody to know this. Has anybody got their ears pierced? What did you put on your ears after you got them pierced?
Earrings?
Alcohol? Has anybody ever used hydrogen peroxide? Yeah, hydrogen peroxide. That's actually what H2O2 is, hydrogen peroxide. And so we say that atoms are the building blocks of molecules. Because if you're walking along, you can identify a molecule by the atoms, and it's unique. Like every single hydrogen peroxide molecule is going to have 2 oxygens and 2 hydrogens. Every single time you drink water, that water is specifically identified by oxygen and 2 hydrogens, by the Mickey Mouse molecule. Numbers are exactly the same way. Numbers are specifically identified. The building blocks of molecules are atoms. The building blocks of all numbers are prime numbers. And so that's why they're really, really special. Has anybody ever bought anything or had your parents buy anything online? Did they type in a credit card? How do you know somebody else doesn't use your mom's credit card to buy something without your mom wanting them to?
Because you get a bank notification.
Yeah. You know what? It's actually prime numbers. Have you heard of encryption? So when you go onto a website, there's a little padlock. And that padlock says you are on a safe and secure website, and you can type in your credit card and not have to worry about everybody on the internet seeing what you typed in. Encryption uses prime numbers. And so prime numbers are incredibly important. They are as important as our molecules are for atoms. So complex curvature thing. So science is an idea, and it's what we think the truth is, but it corrects itself and gets closer and closer to the truth over time. So that's science. What's engineering then? Go ahead.
Engineering.
Well, both of you. Go ahead. You first.
Engineering is making something and making it better and better. A good example of
That is perfect. Wow, that's awesome. What are you going to say? The same thing. That's perfect. That's exactly what engineering is. Oh, wow. You guys have some awesome teachers. So, engineering is, like when I first made a boomerang, it didn't come back. So, like the first couple times, but I kept making changes to it, and so engineering is all about a solution to problems. I don't need to know like why this comes back. You know, I don't need to know about the precession of angular momentum and the center of pressure of lift and the off center and the, you know, the fact that there's a torque from. Now, all those things are helpful, and that's science. As an engineer, I just want something that I can throw when it comes back. You know what you call a boomerang that doesn't come back? A stick. And so let me show you why proof is so important. Because even though we've checked up to numbers. Do you think the universe is pretty big?
Yeah.
Imagine, have you ever been to the beach?
Yeah.
Is there a lot of sand on the beach?
Yes.
You know what sand is made out of? It's actually, well, so playing our game, it's made out of rocks. It's made out of tiny little rocks, and most of those rocks are silicon with 2 oxygens, silicon dioxide. So if you're walking along, you know, if you're subatomic self, and you're like, oh, there's a silicon with 2 oxygens. You must be silicon dioxide. Am I on the beach? So is there a lot of sand on the beach?
Yes.
Think about all the beaches on all the oceans of the world. Is that a lot of sand?
Yes.
Now think about all of the planets in the solar system, all the planets in our galaxy, all of the galaxies in the universe, with all of the grains of sand on all the beaches. And now think each grain of sand has got atoms in it. And imagine that number. In the entire universe, how many atoms there are? A lot? We have checked to bigger than that number. Yes. So imagine the biggest number you possibly could, like all the atoms in the universe. We have checked that number, and all the even numbers below that satisfy Goldbach's conjecture. But it's a conjecture. Conjecture is what we say when we don't have a proof yet. We don't know if it's true. We haven't proven it. Just checking things is not proof. The actual formula for how many is actually very complicated. That's the formula for how many regions there are. And so if we don't actually prove something, we don't know if it's true. And so that's why proof is so important. So even though we've checked Goldbach's conjecture up to more atoms and grains of sand in the entire universe, we still don't know if it's true. And that's what mathematicians do, is they actually prove things. All right. Now I'm just going to show you some really cool stuff in math, all right? Yeah, has anybody ever heard of a fractal? A fractal. So if you haven't heard of it, I'm going to show you some. This is a very, very famous fractal. This is known as the Mandelbrot set. And so the fractal is almost part. So here's another example of the Mandelbrot set. So this part right here kind of looks like a bug, doesn't it? Yeah, it looks like a beetle. So what we're going to do, and this actually comes from this equation right here. It's a very simple equation. And so this is actually a really fun game too, because you can actually have this on your computer, and you can just draw a little region and say zoom in there. So let's do that. Let's zoom into that part. Let's pick another part. Let's zoom in there. Let's pick another section. Oh, look. See some little things that look like beetles up there? So let's just pick another region and zoom in. Let's pick another region. Let's zoom in. Yeah, who said that? Yes, this goes on forever. This does go to infinity. What does that look like? It's a smaller version. A fractal is an infinitely repeated geometric pattern. It goes on forever. It gets smaller and smaller and smaller. That's beautiful. So and you can make your own. And I'll show you how to make your own. And at the very end, I'll actually give you some to take with you. So that fractal is very famous, and we'll actually come back to it. This fractal I'm going to show you is one, again, if you're waiting at a restaurant, you ever been to one of those places where you get crayons? And you can draw on the butcher block paper underneath? I love going to restaurants like that because I can draw a really, really big fractal. And I'll show you how to do this. So you start with a triangle, and all you do is you make another triangle smaller in it. So start with a triangle, connect the midpoints, and then you're going to do it again. So there's a triangle. And you just keep doing that. And you can do it again. 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 And now finally your french fries arrive. And you can set aside. And then you eat all your french fries. And you wait for dessert. And you can keep going. And so this will go on forever. So the reason these are called fractals. How many dimensions does a square have? What did I push something?
It gets lighter the more you add.
Thank you. So, how about a line? How many dimensions does a line have? One dimension. It goes in this way. How about a point? How many dimensions does a point have? One or zero. It has no dimensions. It has 0 dimensions. This has 1 dimension. How about a square? Well, we actually call it 2 dimensions because we can move. So it's like, how many different ways can I move? So if I'm on the stage right here, I can move this way, and I can move this way. Now I could also have gone, like instead of going left, I could have gone right. But right is just like negative left. So it's the same way. So I can move this way, or I can move this way, or I can move this way, but that's in only really 2 different directions. Now when I fly my airplane, I can actually move in another direction, can't I? I can go up and down. So that's 3-dimensional. So a cube, now I'm drawing a cube on a 2D board, right? But can I do a visual illusion to make it look like it's 3D? Is it really 3-dimensional? No. But it looks like it is. But in the real world, you can have something that's 3 dimensions. So it turns, does that look like that?
Yeah.
The other one.
It looks like that one or that one. Yep. This one. So they're actually a little bit different. So one face is one of these. But then we actually did this in 3 dimensions. So it turns out the reason we call these fractals is because they have a fractional dimension. So it turns out that these right here, if I were to do this forever, it would have some kind of fraction in between 1 and 2. So this was 0 dimensions, this was 1 dimensions, this is 2 dimensions, this is 3 dimensions. And in between 1 and 2, there's some fractions, right? It turns out that this is called the Sierpinski triangle. It has fraction 1.58 ... a bunch of numbers. So you can move, you can't quite move fully in 2 dimensions because there's some holes. But you can move in more than 1 dimension, right? You could come this way, and you could say, well, I can either turn left or turn right like that, but I can't turn pure left. And so it's got a fractional dimension, so we call it a fractal. And we can do it in multiple dimensions. So this, when I do a Sierpinski triangle in the 3D world that we live in, it's actually 2-dimensional. And you can see it, and I'm going to give you one of these to take with you, take home with you. I brought a whole box of them over there. We'll pass them out at the very end. Now, there's smaller versions of this, but when you hold it on edge, it perfectly lines up as a 2D plane. It actually turns out that this is 2-dimensional. Its fractional dimension is 2.00000000000. When you hear the sonic boom, you'll hear it. And you can actually, if you listen very carefully, so the sonic boom, it sounds like ba-boom, ba-boom. And we had an airplane, didn't we? Wow, we got one up here. Look at that. Does anybody see an airplane anywhere? Yeah. Where? Oh, they're all over the place. So what happens when the airplane, and the F-16, that's what I flew, it can go faster than the speed of sound. And when it does that, you get a pressure wave. You get a sonic boom. That's the ba part that comes off the nose. Because that's all the air moving out of the way and piling up on each other. And then on the back side of the airplane, it kind of You ever been on a canoe?
No.
And you see, if you look, or on a boat, if you look behind the boat, there's a weight behind it. And so the air goes back on the backside. So that's the ba boom. The ba boom. And so it's a double sonic boom. If you ever get to hear a Falcon 9, and sometimes you can hear them when the atmosphere is just right, they launch out of Vandenberg. It's actually got a triple sonic on it. It goes ba ba boom. Ba ba boom. And so you can tell the difference between an airplane and a rocket based on sonic boom. And you can, if you listen very carefully, you can actually tell how long the airplane is. Because the amount of time between the ba and the boom and the ba boom, ba boom. So you might hear it today. Awesome. All right, one more question. Yes, ma'am.
Does it damage your ears?
It does. Well, it can. So if you're close enough and it's loud enough, the overpressure, it can actually, the pressure wave can hit the ear hard enough that the ear can't move out of the way. So particularly like when a bomb goes off, it also makes a sonic boom, a different kind of boom. But if you're really close to that, the amount of it has to do with how much pressure difference there is. You guys have been absolutely awesome, and so on your way out to go see a one-of-a-kind airplane, we're actually putting AI, artificial intelligence, in this airplane. We've got some little 3D Sierpinski gaskets that will make sure you all get one as you leave. All right, so we'll put these in the bag.